First of all, I'd like to thank the Royal Institute of Navigation for giving me the opportunity to speak to you this evening. This is the story of the search for Ernest Shackleton's famous ship, the Endurance, not in the icy waters of the Weddell Sea, but rather in the pages of the logbooks that were kept by Captain Frank Worsley, master of Endurance during the course of the expedition. The Imperial Trans-Antarctic expedition of 1914 was to last great polar exploration expedition from the heroic age of polar exploration. They planned to land at Weddell Bay on the shores of the Weddell Sea, and from there trek to the South Pole, and then continue on, crossing to the Ross Sea, making a full transect of the continent. Three principal protagonists of our story are here on the left: Sir Ernest Shackleton, who was the expedition leader. In the center is Captain Frank Worsley, who was master of the Endurance. And there on the right is Reginald James, who was the expedition physicist and went on eventually to become the chairman of the Department of Physics at Cape Town University. I'll just give a brief timeline of the expedition. I won't go through all of these points. They departed Plymouth on the 8th of August 1914. Now you'll recall that Britain had entered World War I 4 days earlier. Shackleton had offered the ship and supplies to the Admiralty, but they received a telegram, a cable from one Mr. Winston Churchill, instructing them to proceed. They arrived in Buenos Aires on the 9th of October, and there, prior to their departure, they did something that was very important. They rated their chronometers. That is to say, they determined how fast or slow each one was running at a given instant of time, and how many seconds per day each one was gaining or losing. This is chronometers was crucial to be able to reliably find Greenwich Mean Time and thereby longitude. They headed south, and on the 11th of December, the first sea ice was encountered. On the 19th of January 1915, we see in Worsley's logbooks the ominous words, "fast in pack." Now, trapped in the ice, out of sight of land, there would be no standard way of rating the chronometers, and they would begin to drift. The GMT that they were getting from them would become less reliable, and hence the longitude that they would obtain would also be less reliable. For that reason, on the 24th of June, Frank Worsley and Reginald James began a series of lunar occultation timings, basically noting the moment when a star is seen to wink out behind the limb of the moon. And after doing some fairly lengthy calculations, it's possible to extract Greenwich Mean Time from those observations. The situation aboard Endurance became progressively worse, and on the 27th of October, it had to be abandoned. Worsley writes in the log, "Men and dogs sleep on floe." On the 21st of November, Endurance finally sank. Shackleton records this as, at 5 p.m., she went down by the head. They continued to camp on the ice until the 9th of April, 1916, when the floe began to break up and the boats were launched. On the 15th of April, they succeeded in reaching Elephant Island, and on the 24th of April, Shackleton, Worsley, and 4 others set out in the 24.5-foot boat, the James Caird, to make the 800 nautical mile crossing to South Georgia seeking rescue. Eventually, they landed on the 10th of May and successfully rescued all other members of the expedition on the 30th of August. Now, Frank Worsley was born in Akaroa in New Zealand, and for that reason, his logbooks and workbooks are now in the collection of the Canterbury Museum in nearby Christchurch. A few years ago, a group of enthusiasts in traditional celestial navigation became interested in understanding the exact methods that Worsley had used in navigating from Elephant Island to South Georgia. We studied the the pages from the log. We transcribed them, labeled all the numbers, and replicated the calculations, and published the conclusions in the records of the Canterbury Museum in 2018. I had actually visited the museum in 2017 and was given an hour with the logbook. And I found that during the winter of 1915, there had been a number of non-standard, shall we say, navigational sights and reductions being made. Things like ex-meridian sights of stars and, of course, the lunar occultations. Lars Bergman and myself looked at those pages at great detail and wrote up our conclusions and again published them in the records of the Canterbury Museum in 2018. Both of these papers are available free online as PDFs. Now, also in 2018, the Weddell Sea expedition announced that it had plans to search for the Endurance in the early part of 2019. They gave the log position for the sinking as it was given in the Worsley's log, and it was stated that that was believed to be accurate to about half a mile. Well, having looked in great detail at the navigational methods that were being used, I had the feeling that that was just a bit optimistic. But since by now we had complete copies of all of the pages in the log, it was something that we could check. Before we do that, let's just review some of the principles that go into traditional celestial navigation. Suppose it's the 24th of April, 1916, at 12 hours, 40 minutes and 1 second GMT. At that moment, the sun is, just a second, I can't, I couldn't see a number on my slides. The sun is directly overhead at a point 12 degrees 51.5 minutes north, 10 degrees 28.4 minutes west. And I've marked it on this chart, this map here, over here on the left-hand side. That point where the sun is directly overhead goes by the name of geographic position, and it's a point in modern-day Western Mali. Had you been in Western Mali at this time, looked up and seen the sun directly overhead, you would be, you could safely conclude that that you were at 12 degrees 51.5 minutes north, 10 degrees 28.4 minutes west. If at that time, however, you had noted that the sun was 20 degrees off the vertical, in other words, the zenith distance of the sun was 20 degrees, 70 degrees above the horizontal, then you could conclude that your position lay somewhere along this first circle that I've drawn in orange and written and labeled with 70 degrees. Similarly, if you looked up and saw the sun at a zenith distance of 40 degrees, 50 degrees above the horizontal, you could conclude that your position lay somewhere along the second circle I've labeled 50 degrees. These circles go by the obvious name of circles of position. On the scale that you're typically interested in for the purposes of navigation, you're looking at a very small segment of these circles. And on those sorts of scales, these circles appear straight and they're given the name of lines of position. Now, this first circle labeled 70 degrees, how big is it actually? Well, it's 20 degrees in radius from the geographic position of the sun to that circle. There are 60 minutes of arc in a degree, so this first circle in angular measure is 120 arc minutes. A nautical mile is defined as the distance on the Earth's surface subtended by a minute of arc. And so this first circle here, you see, is 1,200 nautical miles in radius along the Earth's surface. Now, to measure the zenith distance of the sun, you take a sun sight using a sextant, as I've shown sort of diagrammatically here. In practice, you don't actually measure to the center of the sun. You typically measure either to the upper or lower limb of the sun. But once you've taken that measurement, there are a number of corrections that need to be applied. The first of these is the dip of the horizon. because of the curvature of the Earth, the actual sea horizon that you see falls below the horizontal by an amount that depends on the square root of the height of your eye. And that's something that needs to be accounted for. Any body that you see in the sky, any celestial body, is elevated by an amount that depends due to the refraction in the Earth's atmosphere. And so that's an additional correction that needs to be allowed for. If the body that you are measuring is the sun or the moon and you're measuring to the upper or lower limb, you need to account for the radius of that body or the semi-diameter of the sun or the moon. For some bodies, you need to account for parallax. And these bodies are, for example, the sun, the moon, Venus, and Mars. Now, I don't know about you, but it somewhat blows my mind that a measurement made with a handheld instrument like a sextant is sensitive enough to be able to detect the parallax of Venus and Mars under certain circumstances. A final effect that needs to be accounted for if the body that you're measuring is the moon is something called augmentation. As the moon rises from the horizon up higher into the sky, it's actually getting closer to you. So its apparent angular diameter in the sky is increasing. And this is something that needs to be accounted for. All these corrections are in the vertical direction. And so they are taken together, they simply amount to a single number that needs to be applied to adjust the raw sextant reading. Now look at this black dot here on the edge of this map. This is Captain Frank Worsley standing on Elephant Island. In a few moments, he will depart in the James Caird on the 800 nautical mile crossing of the South Atlantic to South Georgia. And he succeeded in getting a time sight. This was extremely fortunate, for it meant that he could more reliably fix his chronometer error and more reliably determine GMT and hence longitude during the course of the crossing. He's measured the sun at 8 degrees, 21.5 minutes. And as you see, it lies just outside that 10-degree circle. Now, this framework of celestial navigation that I've described to you here is not the way Worsley would have looked at his navigation. This is in 1914 and 15, this was still known as the new navigation. We do see a couple of places in the log where Worsley is giving this a go, but by and large, this is not what he was doing. Worsley was principally taking two sites. The first of these is still an important site, known as the noon site. Effectively, what you do is watch around noon as the sun approaches the meridian, rises higher and higher and higher, eventually comes to a halt and begins to fall back. You note the maximum altitude that it reaches and apply the corrections I described on the previous slide. You subtract that number from 90 degrees to get the zenith distance and simply add the sun's declination. Here's the formula here. Very, very simple. And you read the sun's declination from the Nautical Almanac. The other kind of sight that Worsley was performing was the time sight, and that in order to get a quantity called local mean time. The map that I've shown here on the left-hand side shows the situation on the 7th of May, 1916, as the James Caird is approaching the coast of South Georgia. What you, P is obviously the pole, X is the geographic position of the sun, and Z is the James Caird. This dotted line is the meridian that is being drawn from the pole through the James Caird and up to the noon position of the sun. What you want to do is determine this angle labeled LHA for local hour angle. Measuring that gives you a quantity known as local apparent time. Effectively, this is the time that a sundial would show. But unfortunately, it's not something that you can measure directly with sufficient accuracy for it to be useful for navigational purposes. Instead, what you have to do is measure the three sides of this triangle drawn on the Earth's surface, the spherical triangle, and from those lengths of sides, calculate the angle LHA. Well, this side, PX, is known as the polar distance, and it's just 90 degrees plus the sun's declination. This side, PZ, is the co-latitude, or complement of latitude, 90 degrees minus the latitude. You know your latitude because you've been keeping careful track of it by dead reckoning since the last time you were able to get a moon sight. The side XZ is the zenith distance of the sun, which you measure using your sextant. Once you've got the angle LHA and hence the local apparent time, you convert that to local mean time by subtracting a quantity called the equation of time that you read out of the Nautical Almanac. Now, a modern navigator, to calculate this angle LHA, would go to their favorite textbook on spherical trigonometry, extract the cosine formula, plug in various values, and get a form that looked like this. Then he'd get out his calculator and find the answer. Now, in Worsley's day, though, these calculations were being done manually using log tables. And so they had to be arranged into a form that was optimal for evaluation using log tables. In particular, this equation here can be rearranged into the form that you see down here. And you notice that the right-hand side of this equation consists of the product of four trigonometric functions. So this form of product of functions like this is something that can be efficiently evaluated using log tables. So having armed with the knowledge of what it is that Worsley was doing with his sites, let's actually look at the log entries around the time of the sinking. So here they are. Here's the note on the 21st of November that records the position of the sinking. And you'll notice that there are no actual navigational sites made on that day. The previous sight to the sinking occurred on the 18th of November, 3 days prior, and then there's a sight the following day, but no actual observation on the sinking. So what are these various figures? Well, this bank of figures over here on the left, that's an AM time site, the morning time site. So you can see that he has labeled this as AM, and he's drawn this little icon here, a disc with a line under it, and that is telling us that he's measured from the horizon to the lower limb of the sun. These four rows here correspond to the four terms in the product in that formula I showed you on the previous slide, and here he is adding them up to form that product. This column of figures on the extreme left he's doing a comparison of local mean time with Greenwich mean time, and he's getting his longitude. He's doing the same thing for the PM time site. And then this little bank of figures here down on the right is the reduction of the noon site. And as you can see, it's just some very simple arithmetic. He's written the position he obtains from these observations, and he's double underlined them, meaning that they are obtained by observation, not by some sort of estimate. The same format is followed here down here on the 22nd. And here's the noon sight. But there's something rather unusual about this noon sight. I'm sorry, there's an image that is obscuring parts of my slide that I can't see. So anyway, this little bank of figures here at the bottom right is the noon sight. But you see, there's something rather unusual about that. He doesn't seem to have completed the sum in the way that he did up here. He seems to have got so far into it, decided he knew what the answer is, and written the final answer up here. Now, because this is rather important, I've just replicated these figures here and labeled what each of those quantities means. In order to determine his latitude, what Worsley needed to do was add these two rows. The trouble is that when you add those two rows, you don't get 68 degrees 38 minutes 30 seconds. This is recorded here in the log. You get 68 degrees 39 minutes 30 seconds. And that is a nautical mile to the south of the position he's given in the log. So it does seem that there is an arithmetic error here, and that the true position of Ocean Camp is actually at noon on the 22nd, is actually a nautical mile further south than entered in the log. Now, let me emphasize that these are the positions of Ocean Camp. Let's look at the position of Ocean Camp at noon on the 22nd and compare it to the position he's given for the sinking. And when you do that, it's a simple matter to see that this position given for the sinking is just 1.2 nautical miles to the southeast of Ocean Camp. And that's roughly consistent with what Worsley, what we know about the relative distance and bearing of the various camps. On the 10th of November, Worsley writes, our camp is roughly 2 miles northwest of the position of the ship. And on the 21st of November, Ord Lees writes, there was our poor ship, 1.5 miles away, breathing her last. So it does appear that to give the position of the sinking, Worsley has simply taken the noon position of Ocean Camp and applied a 1.2 nautical mile offset to it. And that's the position he recorded. So this is presumably then not the position where the Endurance sank, but rather it's the position of the hole in the ice that it went through 19 hours after the event. Well, let's back off just a little bit and go back and reanalyze the entries as they appear in the log using modern methods. And when you do that, you get this little chart here I've shown on the left. The black dots here are the actual noon positions as they are recorded in the log. This X is the log position that Worsley gives for the sinking. And as we noted, there's an arithmetic error that in the noon site reduction that would push all true sites further nautical mile to the south. So if that error hadn't been present, this X would have been drawn a nautical mile to the south or somewhere around here. So what we've done here is to go back and look at the raw sextant observations and draw lines of position for each of those. These are these little segments of circles of position that I described earlier. This dotted line here is the line of position at the that I get from the morning site, a time site on the 16th of November. Here's the line of position I get from the noon site, and so on. The bars, these gray bars, are 1/2 nautical mile wide in order to indicate the type of error that one gets from sextant observations. Now, we can learn a number of things from this. Well, first of all, the ice is in constant motion. We know actually that the motion of the ice, the drifting of the ice, is dominantly determined by the strength and direction of the wind. This line of position here, labeled 22 AM, is, we know that Ocean Camp on the morning of the 22nd, the day following the sinking, lay somewhere along this dotted line. And in the evening, afternoon, it lay somewhere along this dotted line here. Now, looking at those two lines, you would suspect that the ice had drifted to the west. In other words, there was a net easterly component to the wind blowing over that period. The other thing that you would note is that there's a very large difference in the noon position on the 22nd and the noon position on the 23rd. And that would suggest that there's a pretty strong southerly wind blowing the ice towards the north. So is this consistent with what we know about the wind around that time? Well, on the 21st of November, Shackleton writes, a south-southeast fair wind all day, and later he says, the wind veered later to the west and the sun came out at 9 p.m. Ord Lees on that day says wind south to southwest, increasing about 6 p.m. On the 22nd of November, Ord Lees, who was the expedition quartermaster, records, a moderate southerly wind also bodes well if maintained, though our position today showed that as yet we were neither north nor west of where we were 3 days ago, but had been unable to get a sight since then, and may have made some southing in the meantime. So Ord Lees is expressing the idea that at noon on the 22nd, they're not as far north as he had expected them to be. And he attributes this to them coming from a position further south of where they now are. So what can we conclude from this? Well, there does seem to have been some variability in the east-west component of the wind, but there does seem to be a fairly steady southerly wind blowing. And so from this, we can conclude that the position reported in the log for the sinking of Endurance is based on an offset applied to the noon position of Ocean Camp the following day, and that's 19 hours after the sinking. It is, however, the first moment that Worsley had a complete round of sights with which he could actually reliably fix their position. The reduction of the noon sight contains an arithmetic error, and that has the effect of pushing all true positions a further nautical mile to the south of the ones that appear in the log. And then finally, just to reiterate, it does appear that there was a pretty steady wind blowing from the south over the period from the sinking to the noon the following day. Putting all this together, we can conclude that the wreck could lie to the south of the log position by up to 5.5 nautical miles. Lars Bergman and myself wrote this up and published our conclusions in the Journal of Navigation. Well, that's latitude. What about longitude? Well, longitude should be thought of as the difference between Greenwich Mean Time and local mean time. Each hour of difference between local mean time and Greenwich Mean Time corresponds to 15 degrees of longitude. And as I noted earlier, local mean time is you get by taking a time sight with your sextant. Greenwich Mean Time, ideally, you'd like to just read off your chronometer. Well, the Endurance had a total of 24 chronometers aboard when it set out. And if there is an unaccounted for error in your GMT, if somehow you've made a mistake in what your GMT is, how you've rated your chronometers, that has the effect of moving this entire chartlet, all the lines on this chartlet, east or west, left or right. As I emphasized previously, it's important that you are constantly rating your chronometers, determining the chronometer error and the chronometer rate. But in order to do that, you need an external source of GMT to compare your chronometer to. One way of going about this, obtaining GMT, is to make a time sight from a known location. If you look at this equation here, if I know my longitude and I measure local mean time using my sextant, I can obtain Greenwich Mean Time. Another way of obtaining Greenwich Mean Time is to anchor in a harbor which operates a time ball. This image here on the lower right shows the Greenwich Observatory time ball. And that time ball is hoisted up to the top of the mast and allowed to drop at 1 p.m. They don't drop it at noon because the astronomers are just far too busy making observations at that time. But by sighting the moment when that time ball drops, you can, of course, set your chronometers. A third way of obtaining GMT is to time lunar occultations. In other words, you note the moment when a star winks out behind the limb of a moon. I mentioned that I had visited the museum in 2017 and was given an hour with the log. And I suspect I let out a little squeal of delight when I came to this page in the log. This is the page in the log that records the observation and reduction of the first occultation that they timed of the star 42 Librae on the 24th of June 1915. In fact, they timed a total of 10 occultations from the 24th of June to the 15th of September. Because this is the first reduction they performed, Worsley has been rather verbose in labeling the various quantities that he's written down here. In particular, we see that he says here, he refers to Close's textbook, page 192. And if you scour the archives, you find that there is indeed a textbook by one Major C.F. Close on topographical and geographical surveying. And from that textbook, we learn that the method that they have adopted here to do the reduction is a very old one that dates back at least to 1840, known as Raper's method. This method, as do essentially all methods of reducing occultation timings, uses as input the latitude, again measured by a sextant. Here's the latitude recorded at 74 degrees south, and the local time, mean time of immersion, the local mean time when the star winks out behind the limb of the moon. Now, the way Raper's method works, roughly speaking, is that what you want to do is take your observation of the lunar occultation and infer the position of the moon as it would be seen by an observer at the center of the Earth. In other words, a geocentric observer. What you want to determine from your occultation is the geocentric position of the moon. Now, the geocentric position of the moon is tabulated in the Nautical Almanac. It's a function of time. And so you can effectively do an inverse lookup of geocentric position against time and find GMT when the star disappeared. So this diagram down here, the lower disk is the moon as Worsley and James would have seen it. This object labeled S here is the star sitting on the limb about to wink out. And the upper disk that you see here is the as it would be seen by a geocentric observer. And so in order to sort of hopscotch from your observed position to the geocentric position, you need to calculate these two quantities that are unimaginatively named part 1 and part 2. And there they are there, part 1, part 2. Now, Worsley and James actually recorded a total of 4 occultations on the 24th of June on 4 different stars. And from them, they were able to obtain GMT and an estimate of the chronometer error. Each observation gave a slightly different result for the chronometer error. And here they are recorded here. This is a list of the 4 stars. And here we see the chronometer errors that he obtains for each one, and he averages those. James obviously did a completely independent reduction. These are his results here, and this is his average, and the two are completely consistent. From these averages and these observations, Worsley concludes that chronometer X at noon on the 25th of June was running 2 minutes, 1.6 seconds fast, and that it was losing 0.2 seconds a day. Meet chronometer X. This is obviously a boxed chronometer by Mercer with serial number 5229. For most of the time aboard Endurance, this was the working chronometer. It would have been kept, it would have been lovingly cared for, kept in a temperature-controlled environment, wound at the same time each day, so it's the same piece of the spring that's being used. But once Endurance had to be abandoned, this is not something that you can easily keep at a constant temperature, and you would expect that it would begin. For that reason, the role of working chronometer passed from the Mercer to the Smith, which takes the form of a large pocket watch. And this is something that you could keep at a constant temperature if you wore it close to your body. It makes its first appearance in the log on the 2nd of November. We don't know exactly when it became the working chronometer. It must have been sometime between the 27th of October, when Endurance was abandoned, and the 2nd of November, but we don't know exactly when its drift was the one that kicked in. Worsley writes of this chronometer, let me move this. I carried the chronometer slung around my neck by lampwick inside my sweater to keep it warm. There were other chronometers of this type on the expedition, and one was given to Hudson, who was the navigating officer, and the other to Wild. Now, although we know very, very well how the Mercer behaved, because of the occultation timings and ratings, we know very much less about the Smith. And this is important because it's its drift that is operational between the 22nd of November, between the 2nd of November and the 22nd of November, when the Endurance sank. We do have two data points, however. As the ice continued to drift north, on the 27th of March 1916, they sighted to the west something that they believed to be Mount Percy on Joinville Island, near the north of the Antarctic Peninsula. They took a compass bearing. The ice continued to drift north, and then on the 27th, they took a second bearing. This diagram here is something that I've redrawn from the logbooks. You see here, this is the 24th. They take a compass bearing on Mount Percy. They drift further north. They take another compass bearing, and from that, they're able to determine the location of Mount Percy relative to them. And that gives them their longitude relative to Mount Percy, of course. And you see that what they note here, Percy is 10.5 miles or 23 minutes of longitude west of the chronometer. Now, Worsley only has at his disposal a very small chart of this area by Nordenskjöld and Anderson, and he writes that this Nordenskjöld chart was evidently only intended for general public, and thus not the close accuracy of position for Mount Percy necessary to correct the chronometer. And consequently, I will not allow any change to the chronometer in the meantime. Well, nowadays we know where Mount Percy is, and it's actually 11 minutes of arc, 11 minutes of longitude further west of where Worsley thought it was. And so this picture down here in the bottom left-hand corner is something taken from Google Earth. The yellow lines are this triangle you see above. The red is the position that Worsley had for Mount Percy, and the green marker is where we know it to be today. Based on the modern position of Mount Percy and Worsley's observations, we can conclude that on the 24th of March 1916, the Smith chronometer was running 2 minutes, 16 seconds slower than Worsley had actually anticipated. Now they continued to drift north until the 9th of April, where the flow began to break up. They launched the boats and succeeded in reaching Elephant Island here on the 15th of April. On Elephant Island, just prior to departing in the James Caird for South Georgia, Worsley was able to get a time sight. As I noted, it was fortunate that he did. It allowed him to get a better handle on his chronometer error, and hence Greenwich Mean Time, and hence his longitude during the voyage. This diagram, this survey map here on the left-hand side, was drawn by Reginald James. And here's the same area again in the center from Google Earth. We can see that there's not many places that Worsley could have been standing in order to make this time site. He really had to be somewhere on this little promontory, Cape Wild, which as the expedition called it, now known as Point Wild. And so we know very, very accurately where he was taking the time site from. This large feature that we see on the left-hand side of both these images is about Cape Belsham, which is the feature that Worsley was using as his reference point for longitude. So because we know very reliably where Worsley was standing at the moment that he took this time site, we can say that he was, the chronometer error on the 24th of April 1916 was 2 minutes 25 seconds slower than Worsley had anticipated. But that's obviously surprised him. And rather than correct the chronometer with the full 2 minute 25 seconds of error, he says that he will allow 1 minute and 4 seconds more slow. And his justification for this is that the longitude of Cape Belsham, this feature here, is only approximately known to us. And why does he say that? Well, here on the right is the chart that he's using to determine the longitude of Cape Belsham. Now, it's big enough that you can just make out the lump that corresponds to Cape Belsham. Nevertheless, the position that he extracted from this little chart is only 2¼ nautical miles from the position as we know it today, which is quite remarkable. Now, only allowing 1 minute 4 seconds more slow rather than the full 2 minutes 25 seconds is not quite as cavalier as one might imagine. It introduces a bias of 10 nautical miles to the west of the positions that you're going to get. And that has the effect of tending to avoid the possibility of overshooting South Georgia to the east. Had that happened, there would have been no way to beat against the prevailing wind and actually land on South Georgia. As they approached the coast of South Georgia, Worsley was able to get a sight, and from that he concludes that they were about 20 miles of distance further astern than observation showed, and half of that is attributable to the 10 nautical mile bias that he introduced at the outset. Well, so what do we conclude about longitude? Well, there's a clear tendency on Worsley's part to have underestimated how slow the chronometers were running. And this has the effect of pushing all true positions to the west of those that appear in the log. There are a number of provisos and uncertainties that go with this. One is that we don't really know the exact date when the Smith became the working chronometer, and therefore we don't know precisely when it's drift that kicked in. We have some estimates of the long-term trend for the Smith, but that may or may not be a good reflection of the short-term variation. And there seems to be some variability in the east-west component of the wind, which introduces some additional uncertainty. But based on the chronometer errors alone, the wreck should lie to the west of the log, should lie to the west of the log position by up to 5.9 minutes of longitude, or 2.2 nautical miles. A westward drift of the ice, which the AM and PM time sites on the 22nd seem to indicate was occurring, that has the effect of pushing the position back to the east. Now, in the early part of 2019, the Weddell Sea expedition succeeded in reaching the location of the sinking as given in the log. They launched their autonomous underwater vehicles, which were untethered to the ship, and they searched for 30 hours, after which time they lost contact. Unfortunately, the search had to be abandoned because of deteriorating weather conditions, and that meant that no data was obtained. Well, that's a pity, but since there'll never be another expedition to look for the Endurance in my lifetime, I guess we're done with this project. Not quite. We were contacted by David Mearns of Blue Water Recoveries. David is a professional wreck hunter. As Claire mentioned, he'll be giving the EGR Taylor Lecture in October this year. And he's spent many years scouring the archives looking for information which would help pin down the location of the wreck of Endurance. He had discovered a paper, an unpublished paper in the archives of the Scott Polar Research Institute, which showed that physicist Reginald James and A.C. Cromlin, who was an astronomer at the Greenwich Observatory, had corrected the chronometer errors that they'd obtained from the occultations using positions of the moon that were actually observed, not the ones that were given in the Nautical Almanac. And that had the effect of changing the chronometer errors from the occultations by about 20 seconds, making the chronometer errors 20 seconds faster than they originally obtained. Now that has the effect of pushing true positions to the east of those in the log, in the opposite direction that we described previously. The point here really is that the accuracy to which the moon's position was quoted in the Nautical Almanac far exceeds the accuracy to which it could actually be calculated in advance. So for example, here we see that the position of the moon is being calculated, is being quoted to 1/10 of a second of arc. And here, right ascension is being given to 100th of a second. Well, nowadays, of course, we can calculate the moon's position to tremendous accuracy. So we looked at that. We compared the moon's positions that we calculated using a jet propulsional laboratory model of the solar system, DE430, with the positions in the Nautical Almanac, and we found indeed that the ones in the Nautical Almanac tended to lag the true positions by about 0.9 seconds in right ascension. In declination, we saw a root mean square difference between the true positions and the almanac positions of 1.7 arc seconds, which is far exceeds the 0.1 second of arc accuracy that that it's quoted to in the almanac. We were able to do something else that, of course, Worsley, James and Cromlin couldn't do, and that was to use modern star positions. We found that the star positions that, as they appear in the modern Hipparchus catalogue, differed from the, on average, from the star positions as they were given in the Nautical Almanac by 1.3 arc seconds, with a maximum of 3.2 arc seconds. An additional complication appeared in that the star A Ophiuchi, which is observed twice, once on the 22nd of September and once on the 15th of September, was actually a binary system consisting of two nearly equal components separated by 4.24 arc seconds. The position angle for these two components in 1915 was 184.1 degrees, meaning they were sitting essentially exactly north and south of one another in the sky. That means that the one that disappears first behind the moon's limb depends on exactly where on the moon's limb the occultation occurs, and that in turn depends on where you're observing from. On the 23rd of July, the two stars effectively disappeared simultaneously, separated only by 0.15 seconds. But on the 15th of September, there was a 4.25 second time difference between the disappearance of the first star and the second star. The Nautical Almanac, however, instructs you to time the first star. Now, once you've computed the chronometer errors from the occultations, what would Worsley have done? Well, Worsley would have done what I've shown down here in the bottom left-hand corner. He would plot these observations on a graph against time. These open circles represent the observations, and then he would have drawn a line of best fit through the observations. Ignore this point for the moment. This dotted line is the line of best fit, and its slope gives you the chronometer rate. This solid point here is the chronometer error that you deduce for the 27th of October when Endurance was abandoned. It's not something that goes into the fit, you only fit these open circles. So we can take the line of best fit and we can plot the difference between the line and the actual observation as a bar graph. This difference we're going to call the residuals. And so I've done that here. These, if I plot as bar graphs the difference between the line of best fit and the actual observation, I get these orange bars here. And I can do the same thing with Crommel's corrected observations, and the residuals are these blue bars here. If I then look at Worsley's observations using the modern positions of the moon and the stars, the residuals are these much smaller green bars here, which tells me a couple of things. It tells me that the Mercer was behaving very nice and linearly, as a good chronometer should, and that Worsley was doing a very good job in taking his sights. The real limitation that he faced was uncertainties in the position of the moon and of the stars. So let's look at what we get from fits to these various types of data. Using the original data, we get a chronometer error for Worsley on the 27th of October 1915, at the time the Endurance was abandoned, 2 minutes 45.5 seconds fast, and a chronometer rate here. Using the modern data, we get a chronometer error that is a fair bit larger, and also a chronometer rate that is larger. Now we can ask the question, how good is this linear fit? Well, there's a figure of merit that we can use when you do least squares fitting, and that's the R-squared measure. Basically, it's a measure of how much of the variation in the data is explained by the model. It'll be 100% for a perfect fit, and the R-squared for Worsley's observations using the modern data is a very, very respectable 99.2%. So what do we conclude for longitude now? Well, Worsley's tendency to estimate how slow the chronometers are running still pushes true positions to the west of those in the logs, but now we have an unaccounted for chronometer error of 28.9 seconds fast, and that pushes positions, true positions, to the east of those in the log, and these two facts are working against one another. We still have these three provisos that I noted before. I won't go through them again, but based on chronometer errors alone, we're able to conclude that the wreck should lie to the east of the log position by up to 2.4 2.4 minutes of longitude, or 0.9 nautical miles. If the drift that we observed, the westward drift of the ice that we observed during the day of the 22nd, is extrapolated back 19 hours to the time of the sinking, and that's uncertain. As I say, we do think that there's some variability in that east-west component, but if we do extrapolate it back, that could push the position further to the east by a further 2.6 nautical miles. Well, that's very interesting, isn't it? But since we know there'll never be another expedition to search for the Endurance, maybe we'll get around to writing it up, maybe we won't. Well, now, in 2021, the Endurance Endurance22 team announced that they were indeed going to make another search for Endurance. And this time they weren't kidding. They had Saab saber-tooth drones that were tethered to the ship. They had a helicopter that could ferry them to an ice camp if the ship couldn't reach the search location. And so it became apparent that we needed to write up these new results. We submitted the paper on the 29th of July, 2021, where it remains a year later under review to this day. In early February, it became apparent that we needed to circulate these results, and so we made it available as a preprint at this. On the 5th of February, the icebreaker Argulis left Cape Town with a search permit allowing it to look for the Endurance until the 10th of March. On the 5th of March, they announced that they had found Endurance. So where? Well, there were mutterings of it being 4 nautical miles to the south or southeast. But let's look at the actual AIS data for the ship. And this was a very nice chart made by this gentleman down here. And he superimposed it on this little chartlet that I show you here. So here's the 4th of March. And then the 5th of March, going slowly along here. And then they go on the 6th of March, they go up here, they come back. And on the 7th of March, they execute the slow zigzag here. And then they go home. Well, don't know about you, but if it were me, I'd guess it was somewhere around here. Well, we had to wait until late June before the exact position was disclosed, and here it is. So where is that in this little chartlet? Well, here it is. It's in that little zigzag that we saw them executing. And that is a position that is 4.9 nautical miles south and 2.4 nautical miles to the east of the position as given in the log. And that, ladies and gentlemen, I would contend is entirely consistent with where the entries in Captain Frank Worsley's logbooks were telling it would be, as it would be. Thank you very much.